Yeah, thank you very much for inviting me to share this work here. So in this talk, we are going to introduce one of our recent work about basically combining this tissue suppression with blood-nulling to improve some technique we developed before, like called VAPER. This time we combine the tissue suppression into this sequence to improve the contrast and sensitivity. And you can hear me okay, right? Okay, great. So, so I think everyone here knows that in layer-fMRI, CBV, CBF is more, it has a bad specificity compared to both because both has genuine effect, and the CBV, CBF can localize like a laminar activity like more specifically. And so this is the advantage of CBV, CBF based fMRI like over both. But the limitation of like CBV, CBF based fMRI, the issue is their relatively poor sensitivity compared to both. So for example, like here, for example, like a CBV based fMRI, like VASO, or the technique we are going to focus on today, like VAPER, their sensitivity is less than half of both. So in the original sequence design, like a VASO VAPER, if we compare to both, like a both here is the T value inside the activation region, so the same RI. For example, for both, the mean T value like around 6, 7, but for VAPER is around 2, VASO is around 2. So the sensitivity is around 1/3 of both. And in CBF based like in SL, their sensitivity is even low, it's like 10 to 20% of both. So it's even low. And so in this talk, I'm going to show you if we can improve those CBV based fMRI sensitivity for layer-fMRI. Oh, sorry. And in CBV-based fMRI, like we usually, for CBV waiting, to do that, we will need a blood-nulling in the sequence. Like in VASO, people are usually use like infusion recovery because of the T1 difference in tissue and blood. So you can add infusion and then wait some time, like when the blood cross 0, you can measure the residual tissue signal. So this signal will be sensitive to CBV changes. Or like in VAPER, we use DANTI, which is a flow suppression module. So it can suppress the blood and we can measure the residual tissue signal. It can also be sensitive to CBV changes. And in fMRI, like so this is for the VASO or for the infusion recovery or the DANTI is a preparation. For the acquisition part, we typically use EPI because it's more time efficient. And for EPI, it will inherently like sensitive to T2 star changes, which is bold. So if we like have both CBV, CBV and bold will dominate over CBV. So we will need to like so in addition to the blood-nulling, like those kind of condition acquisition, we will interleave it with a control acquisition, which is bold acquisition. So in this way, we can like compare those two to first remove the bold because their acquisition is identical. So you can factor out the bold T2 star term and then extract the CBV like weighting. And for this control part, like if we don't consider bold, so we add like a control measurement into those like a VASO sequence or VAPER sequence because for the purpose of bold correction. But if we ignore the bold here, so if you compare those blood node versus not node, so if a blood is not, consider this as like for example graded matter voxel, like tissue will have like 90. It will contribute about 95% of the to a voxel signal, and blood contribute about 5%. So if you now blood signal, this voxel signal becomes 1 minus CBV. And for the in the control condition, so in a control condition, if we don't consider any kind of like saturation, like a steady state, just like the initial like state, like the voxel signal is, so in a control condition, there's no suppression at all. So the voxel signal will be 1. And so in our phasal sequence or in VAPER sequence, we combine those two. Basically, the CBV term is still same. It's the original CBV term. So the control condition will we will not add any additional CBV sensitivity. It's just like added because for the purpose of border correction. So it doesn't add any additional like sensitivity. So the ideal here is instead of doing like interleave for those acquisition of both node and non-node, we instead of doing like those control, we replace this with a tissue suppression. So in the blood node condition, if we node blood, the voxel signal becomes 1 minus CBV. And in the every other volume, we suppress tissue. So the blood will not affected, but the tissue will be suppressed. So if a tissue is fully suppressed, this voxel signal will become CBV. But because like some other limitation, the tissue will be like basically partially suppressed, so it will become this term. And if we combine, take the difference between those two and ignore the constant term, the CBV term will become like this. So if a tissue can be fully suppressed, this CBV sensitivity will be doubled, will be 2 like multiply CBV, so it will be doubled. But because of like some limitation, like side limitation, basically this term will like in the range between 0 and 1. So, but still this term like will be increased by some percentage of the original when you interleave with blood node and control. So this is ideal. Instead of doing a blood-nulling first control, we here in this talk, I'm going to introduce like the idea of like interleave the acquisition between blood-nulling and tissue suppression. And theoretically, if the tissue can be fully suppressed, this CBV sensitivity will be doubled. I hope this idea is clear to you here. And so how to do this like in the scanner? And so to acquire this signal in the scanner, we will basically have like 2 condition acquisition. Like one is the blood node. For the blood-nulling, we use like a Dante pulse, which is a velocity selective suppression module. It can like suppress blood faster than 2 millimeter if the blood is flowing faster than 2 millimeter per second. And in human brain, if we break it into different compartments, like large vessels, arteries, veins, small vessels, arterioles, venules, they are fast. They are flowing faster than 2 millimeter per second. So they will be directly suppressed. And in capillary, their blood flow is kind of very slow, like slower than 2 millimeter per second. It will not be directly suppressed. However, this pulse is kind of like a should do continuous, like in infusion recovery, you apply it like as a one shot. You apply once, for example, in the original sequence design, you apply once at the beginning and then acquire all your like slice. But for the Dante, basically we apply it before every excitation shot. So it's kind of like a should do continuous like suppression. So this blood will continuously suppress during your acquisition, and this suppressed blood will flows into capillary. So the capillary blood will also be replaced by the suppressed blood signal. And because some other effect like a permeability exchange between tissue and the capillary, in the end the capillary blood will like will result in the middle. But relatively the blood signal will be like the red curve will be suppressed compared to tissue signal. And I hope you can like remember like in CBV based fMRI, CBV changes is mainly contributed by arterial part because of 2 reasons. First is the T2 star. T2 star is relatively longer in arterial compared to capillary and venule, so it will contribute more to your final fMRI signal. And second, the blood vessel dilation ability like is the strongest in arterial. So arterial contribute most of your CBV changes. So in this way, for the arterial blood signal is basically fully null compared to the tissue signal. So this is one condition, blood is suppressed. And in other condition, like we want to suppress tissue signal. So here we use the MT like approach to suppress tissue signal. And for MT approach, typically in the scanner, we will use like apply a single and very strong off resonance like a Gaussian pulse to do that. But at 7T, that's not very size efficient. So instead of that, we are using very small Freiberg angle like a 10-degree IF pulse. But and instead of off resonance, here the IF pulse are on resonance. So small Freiberg angle, on resonance, and binomial IF pulse. And we apply like hundreds or even thousands of those kind of small Freiberg angle IF pulse. And the pulse interval is like smaller than 1 milliseconds. Typically, in our study, we applied those IF pulse every 200 microseconds. So 0.2 milliseconds, we apply one those kind of pulse. So you can think of, for example, in 100 milliseconds, we could apply 500 those kind of pulse. So a lot of those kind of small Freiberg binomial pulse. And because the pulse interval is very short, it's like several hundred microseconds. So it will selectively saturate the short T2 component, which is like so in our, for example, in brain, like the large molecules, basically they have a very short T2, like smaller than 0.1 milliseconds. So those like a large molecule, the signal from those large molecule will be suppressed. And this basically this large molecule basically mostly stays like in tissue, like in gray matter, white matter, and in blood it has very less like those kind of large molecule. And because of some MT magnetization transition effect, this saturated like signal will transfer into water. So basically tissue signal in this way, tissue, because it has most of the large molecules, it will be selectively saturated, suppressed by this MT binomial pulse. So if you want to understand it, you can also understand this pulse in another way if you do a block simulation of those pulses. Also, this IF pulse is applied in our own resonance way, but if you do a block simulation, basically it has a lot of saturation band at some off resonance frequency, which is determined by your pulse interval. So it basically quite similar to the original like off resonance like MT pulse. But generally we use this MT binomial pulse for the tissue suppression. And so in our acquisition, basically we will have those two conditions. In the top row, we have the dentate blood suppression. In the bottom, we have MT tissue suppression. So in the dentate blood suppression, it will suppress the blood signal, and your tissue will be like relatively less affected. So in this simulation, the blood signal, like the red curve, will be fully nulled, but the tissue signal will be relatively less affected. And in the MT tissue suppression, so in the top, like blood is dark, is suppressed, the tissue is white, is less affected. But in the bottom, in the tissue, in the MT effect, is kind of opposite. So tissue will be suppressed, and the blood signal will be very weakly affected. If we do a simulation of this effect, like the red curve, the blood signal, like the arterial blood signal, it will be very weakly affected by the MT pulse. But for the tissue signal, like the blue curve, it will suppress that to a low level when you apply the more and more pulse over time. So theoretically, if we are not limited by SA, basically we can apply more and more MT pulse to suppress the tissue to a very low level, and at the same time, the tissue still stays as a very high signal. But in reality, because we are doing experiment in human and we are limited by SA, by time, so we will end in the middle, but still like a tissue signal will be relatively suppressed compared to blood. So this suppression effect determines how much we can enhance the sensitivity. And you can understand, for example, if you compare those two, so in one condition, in the dentate condition, blood is suppressed, tissue is relatively unaffected. But in the MT condition, blood is like unaffected, but tissue is unaffected, but blood is suppressed. So this CBV contrast is opposite. But at the same time, when we design our acquisition, the EPI acquisition is identical. So the T2 star term, the bold is identical. So if you compare those two, bold is identical. The bold T2 star term like will be identical, but the CBV contrast is opposite. So if we combine those two, basically you can cancel out T2 star bold at the same time, like enhance your contrast, your CBV contrast. So this is the ideal. And we design the sequence. Our fMRI time series basically will be acquired like one volume, we acquire dentate blood suppression. And in the other condition, we apply the MT image, related image. So for example, in the dentate blood suppression, we will apply the preparation before every excitation shot. So the blood signal will be suppressed as here, like showing the simulation in the red curve. So the blood is suppressed, but the tissue is relatively high. So you will sensitive to CBV changes. And in the MT condition, the MT pulse, so in the MT condition, we only need to switch off the dentate gradient. This preparation will become like a binomial pulse, and then maximize your IF like power, because MT effect is basically determined by IF power. So we will basically push the IF power to as much as allowed by the scanner. And so in the MT condition, like after the dentate, in dentate, the blood is suppressed. So, and remember at 70, like we are using head only coil for RF transmission. So in the dentate condition, the blood is only suppressed inside your head. Outside of your head coil coverage, like in your neck, in your body, the blood is fresh. So it will flows into your brain like after dentate condition, and arrives your image region at around the arterial transit time, and then perfuse into your image region. And here our like repetition time is around like more than 4 seconds. So like after the dentate and then reach the K-space center, basically it has like more than or around 2 seconds. So this fresh blood will have enough time to perfuse into your image region. So you will have perfusion waiting. At the same time, the MT will suppress this tissue signal, like here, like the blue or like a blue curve. So you will have like a suppressed tissue signal relatively dentate condition. If there's no MT, this tissue signal will recover. But because of MT, it will suppress this tissue signal. So it can maximize this like blood and tissue, this ratio like even more. So you have additional CBV waiting. So here you have a CBV waiting, like in dentate, you have like a CBV waiting in MT, and also perfusion waiting in MT. And in our analysis, basically, original time series is alternating between dentate condition, MT, dentate, MT. In our time series, like to generate the vapor, like we basically do a division, like a dynamic division, like between MT and dentate. And because those two, they have identical T2 star term, so this T2 star term will be factored out. So it can remove both contribution. At the same time, their CBV, so CBV contrast, those CBV contrast is opposite. Also, like the CBF is only in the MT. So you will have like a very enhanced like intravascular contrast after both correction. And the bottom shows the image. Image like the first is the MT like EPI image. We add term bold because this MT image, the signal change from this MT image, like fMRI signal from this MT image, is mainly dominated by bold, so we call the MT bold. And you can see in this image, those like marked by the purple arrow, basically showing the blood signal. So the blood will not be affected by MT; they are still bright. And the tissue. So theoretically, you could suppress it to a very low level, but you are limited by the SAR. So you suppress your tissue signal to some level, and you can tell from this gray matter, white matter contrast, because MT effect is different in gray matter and white matter. So, and in the dentate image, in the dentate EPI image, those blood signal which is bright in MT image becomes dark in dentate image because the blood is suppressed. Yeah, and the tissue signal is relatively unaffected. And we combine those two, we will generate an MT vapor image like this. It has a relatively good like tissue contrast between gray matter and white matter because of the MT effect. And the right shows the TSNR of MT, like a bold image and the MT vapor image. And you can see in this vapor image, the TSNR is also quite good compared to like a bold. It's relatively low, but it's still comparable. I would say it's quite good. Yeah. And here is a simulation of this MT vapor signal. So we simulated MT vapor signal change like as a function of CBV change, CBF change, and basically you can see like in the range of, so we simulated CBV like from 0 to 100, CBF from 0 to 200, because at a high resolution there are some like in some cases, in some workflows, when it is dominated by those vessels, it has a very high like CBV, CBF change. So we simulate all those kind of extreme cases. And generally, like a MT vapor signal change will be in the range of a few percent, like and here, for example, in the middle is around probably 2% signal change. You would I will show you later, like our results matches this quite well. And basically, this MT vapor it will be sensitive to both CBV change, CBF change. And the right shows like how much MT can enhance those vapor contrast. So basically, we simulate this like one with MT on, the other with MT off, and then compute. So at a different CBV changes, CBF changes, in each plot we compute how much vapor contrast can be enhanced by MT. And you can see in those bottom right, those kind of triangle in those region, MT has a very weak like effect because this is CBV sensitivity. So MT has a very weak like MT almost has no effect on the sensitivity or to CBV. But on the up like those like up like a triangle region, in those region, you can see MT really enhance their sensitivity like to CBV. And this is as we predicted, because in the model, basically MT improve the vapor sensitivity is mainly because of it's like improved like sensitivity to CBV. And typically in a typical region, for example, CBV, like in this region, CBF in this like here in our in like a brain activity, usually like so based on the simulation, MT application could improve the contrast by 50 to 35%. And this improvement is achieved primarily because of the increased CBV sensitivity. This is a simulation tells us. And this slide basically, I show you some like experiment like to like demonstrate to see how much like MT can enhance the sensitivity. And here we applied the sequence like to a relatively large brain coverage. And we show the present the subject with some like check bottle stimuli and acquire the image at a resolution of 0.8 millimeter isotropic. And here is the bold activation map. And the bottom shows the vapor activation map. The vapor signal is after like a dynamic diffusion. And this activation map is got without any smoothing. So you can see it's quite good. And the right shows the T value, mean T value in the bold activation region. So we calculate the bold vapor T value inside this activation region. They have the same ROI. And we also compared with the original vapor, which is the MT preparation is turned off. And you can see relative to bold, vapor sensitivity now is around 46% of bold. This is very close to half of the bold sensitivity. And at the same time, if you compare MT bold with the original bold, basically MT could improve the sensitivity by 29, around 30%, which also matches our simulation. So it could MT here could significantly improve the sensitivity of the vapor sensitivity by 30% around. And at the same time, like this MT vapor also has a quite good laminar specificity. Here is like one subject, and we ask the subject to do a finger typing task. So, and here is like one measurement. The bottom is another measurement. In the activation map, you can see those like two stripes like here. It's very clear. And if you try the laminar profile in this ROI, you will see two bumps. And in the border, you can, so you can also see a little bit like a second bump, but I would say the superficial one is like a much stronger. So those kind of double peak feature is much more clear, like in the VAPER image compared to bold. And these results we tested like in also across different subject is very consistent across different subject, and each subject we tested across different measurement is also consistent. So this is a short summary of the previous part. So in those like in this laminar fMRI in motor area, it has like one issue. Basically, we need to draw this ROI like manually. So they are, and in layer-fMRI, basically people do a lot of those kind of manual ROI definition or a lot of those kind of manual correction of like a grid matter, white matter boundary. And because of this, we have received a lot of criticisms of those manual ROI definition or manual correction. Because even using the same data, different research can draw layer ROI differently, which will lead to, variations in laminar profile. And those inconsistent ROI definition could result in different interpretation of laminar activity pattern. Even the same layer like activity pattern, if you draw your ROI differently, your layer profile is dramatically different. Your interpretation of the data will be different. And also those like a manual collection is very time consuming. Here we only focus on a small region like the motor cortex. If you think about like if you want to do a whole brain layer-fMRI, it could take you forever, either all of your like work time. And it may also make it very difficult for other researchers to repeat the findings. So to address this issue, we applied our sequence to visual cortex, because visual cortex has a very well-defined retinotopic like a retinotopic mapping. So you don't so you can use that information to define your ROI very accurately. For example, here this one is bold activation mapper, this one is VAPER activation mapper. If we need to extract the laminar profile in different visual area, we don't need to draw the ROI manually. We can just based on the retinotopic atlas to do that. For example, here the underlay here, I forgot to say the underlay here is an empty EPI image. It already have a very good grid matter white matter contrast, so we can feed this and this EPI like anatomical EPI. Because it has identical acquisition as function, so we can feed this EPI image directly to free surface. It will generate the cortical surface and grid matter, white matter boundary, and we can grow our layers all automatically. And for the ROI, here we define V1 with eccentricity less than 10 degrees based on the Benson like retinotopic atlas. So it can be defined automatically. And this V1 and also eccentricity less than 10 degrees is our visual field, is also within our visual field. So in this region, we can extract the laminar profile like red curve is the bold. You can see it basically, it has a very strong bias toward the cortical surface. Cortical surface has the strongest both signal change and then decreases toward the deep layer. But for the VAPER, you see in the superficial, the signal change goes down. So the peak is more close to the middle cortical depths. And this result is also consistent across different individuals. So each plot is from one individual, and you can see the red curve is bold, which is biased toward the cortical surface. But for the blue curve, which is VAPER signal change, is more it has so the superficial bias is less and is more close peak to the middle cortical depths. And this is a summary of the previous of this talk. Basically, we add IMT to induce some tissue suppression effect and incorporate it with the original VAPER to boost the overall sensitivity. And for our acquisition, we instead of doing a blood-nulling for the not-node, we do a blood-nulling for the tissue suppression. And this way, we can enhance our sensitivity by around 30%. And we demonstrate this sequence like application like for laminar fMRI in motor cortex and visual cortex. And I have a few more discussion slides. So here, like we define our ROI in V1 with eccentricity less than 10 degrees. which is like our stimulus visual field. How does the laminar profile looks like outside of your visual field? So we submitted this work to some journal, but we didn't include the last discussion part because we don't know how to understand these results. But I want to show to this group for some discussion. So in the V1 with electricity less more than 12 degrees, so outside of our visual field. So inside the visual field, there's a Chagabala stimulation. Outside of a visual field, like in this region, and here is the bold signal change, vapor signal change, across cortical depths. 0 means cortical surface, 1 means like deep cortical layers. You can see both bold and vapor, they have negative signal change. They have a negative signal change. And the laminar profile, both of them like peak in the superficial layer. I don't know how to understand these results, but we know like outside of your visual field, the stimulus visual field, there will be a surrounding suppression. I'm not sure if this like the laminar profile the peak in superficial reflect this surrounding suppression effect. Surrounding suppression should cause this like negative bold, negative vapor, and maybe this like superficial peak could reflect some meaning of the surrounding suppression, but I'm not sure. And in negative bold, we know like it also have some like a quite complicated like a physiology mechanism under it. For example, the relationship between CBV, CBF bold is kind of different in positive and negative like range. For example, I borrowed one slide of some results from like a previous Joseph's paper and also some like a figure from previous Peter's like paper. So like in positive, like if you look into the visual cortex, like in the positive activation region, like body is positive, CBV is positive, CBF also positive, but both because of the genuine effect, it peaks in the superficial. CBV, CBF, it peaks in the middle. So it's and the low signal, if you combine it together, it will not cancel each other. But in the negative part, it becomes quite complicated. Like a bold is it has a negative change, and also the peak seems goes to the superficial. And in CBV is kind of complicated. It still has like in this paper, at least in this paper, CBV still has positive changes, like a peak in the middle. But I would say like in the closer to the superficial, you kind of also has some like a negative part. And in CBF, you has a negative change and peak to the superficial. And this is some like a diagram show the relationship of those. So in positive bold, bold itself, you will peak in the superficial, and the CBV, CBF, they peak in the middle. But in the negative bold, CBF will peak in the superficial. CBV will peak in the middle based on this work, monkey work. But they are also a little bit like negative, I would say, in the superficial. So the relationship is kind of become complicated in the negative bold. There's also a recent publication like from USC group. They measured also so positive and negative like fMRI like so the red curve showing their visual field within their stimulus, which is the red curve. So you see the positive change like close to the middle layer. But outside of the visual field, for example, in full field or in peripheral, like the black curve and the yellow curve, they see they peak in the superficial, but and also in the deep. But it's kind of difficult to tell because the sensitivity is quite low. So in negative bold, it's really not clear like how the laminar profile should looks like. And even so, we know there's a surrounding suppression in visual field, like outside of your visual field. But from the fMRI laminar profile, it could also like include very complicated those kind of vascular like relationships. So let's basically,
Yuhui,
yeah,
can I ask something to clarify? In the previous slide where you show Gönz's work,
yeah.
in here, panel D and G, like the positive and negative are upside down there. And if I heard correctly, you were saying the lower side is negative. Was it?
Yeah, it's negative. Here's negative.
Yeah, but not in the middle.
Sorry. Yeah, that's true.
So does it change the way you interpret? Because I thought you said the other way around. So I was just trying to clarify. Was it like a
Oh, yeah, but it still seems like because the CBV here, because the facial signal is a negative change, so negative will be positive, like a positive bold. So it doesn't. Yeah. Thank you.
Fine.
Thank you. Yeah, that's all I want to share. Yeah. So if you have any questions, yeah, feel free to ask. Yeah.
Thanks, Yuhui.
I have some questions about the beginning. I don't really understand how you eliminate the bolt in the tissue. So
which slide you mean, like
yeah, where you said do before this where you do the equation
like here or here? Which slide?
CBV minus remaining times the remaining tissue.
You mean
Yeah,
this one? This one is like a model. It's not like how we do it actually. I just showing a model how can we generate like a improve the contrast. But what's your question?
But what is the contrast? You subtracted two measurements?
Yeah,
Or?
here I just subtracted.
Yeah, but the tissue has bold too, right?
Yeah, tissue has bold too.
That's not subtracted out.
Yeah, here I as I said, if we don't consider bold here, yeah, if you
But
consider
in reality there is bold, right? So then you have bold in your contrast.
yeah, bold will be our so like when we consider this bold, like so this is a very like simplified model if we don't consider bold. So if we don't consider bold, basically I'm showing like in this figure how can we like amplify the contrast, like so.
Yuhui, I think
Yeah.
the question goes with respect to the analysis. You had later these pink equations.
Yeah. So
Yeah,
for the
ratio.
border correction, we do it in this way. Like in theoretically, we do it in like through a dynamic diffusion. So the border T2 star term like is as a multiply factor. So it will be factor out if you do this diffusion.
Yuhui, like what do you do there exactly? So if I understand correctly, your MT1, so Dante is similar to 1 minus CBV together with T2 star weighting, right?
Yes.
And then MT1 is the CBV together with T2 star weighting.
With some like with some like residual tissue because MT cannot supply all the tissue. So this one MT will be like a 1 minus CBV, and the Dante one will be 1 minus CBV, and there will be some like a T2 star term like multiplied, and the MT one will be CBV plus some residual tissue. If the tissue can be fully supplied, then it will be simple. It will be CBV multiplied by your bold term. But there will be some residual CBV term, residual tissue term, like and then multiplied by your T2 star term. And then we do the diffusion. And then we do the diffusion, those T2 star term can be factored out.
Just to understand, I still didn't understand. So Dante 1 is like 1 minus CBV, let's say, plus some other stuff. I'm just like asking very simply.
Yeah.
And MT1 is like CBV, not again 1 minus CBV.
Yes, CBV. But the MT cannot suppress the tissue. Like if
it's fine. Like I'm just trying to clarify. Like
yes.
1 minus CBV or CBV to MT1. That's what I was asking.
So MT should be CBV. If
okay,
the tissue
then
is
you divide like this 1 minus CBV plus other thing with CBV. Plus other thing, and those other things, which is like relating to T2 star. Weighting, they cancel each other out. This is what you are saying, right?
Yeah. There will also be some CBF weighting, but it will be enhanced altogether.
I don't see how you divide the T2 star out. The T2 star comes from different tissue compartments, right?
Yeah, it
doesn't really divide out.
Yeah. I totally agree with you. So I totally agree with you. If you consider it like a very seriously, because the tissue and so if you consider it very serious like a bold, consider it as intravascular, extravascular bold, because the relatively contribution is different. So it will not be, for example, theoretically fully like corrected, factor out, but mostly like the bold will be factor out.
So the other thing is the Dante, you say that suppresses CBV. I don't really. understand that. So you're talking about arterial blood, venous blood. What is the direction of the suppression? Because it is in one direction, so you don't suppress all directions. So what exactly do you suppress with that? I don't really get that.
There's a direction in a gradient. So in a gradient, we applied in two direction, one in X and Z direction. But for the blood vessel, like in your head, like for example, for the small vessel, for the arterioles, venules, it could has a lot of direction. It goes like all kinds of direction. So and also this blood suppression is a kind of like a dynamic continuous suppression. We applied before every shot. So there will always be a chance those blood will experience some blood suppression. Like
yeah, but we don't really care about the capillary bed, right? Because we want to see that. So you don't want to suppress that.
We also want to suppress the capillary bed. We want
arteries and large veins, right? That you want to suppress. And
we want to suppress all blood signal.
Sorry?
We want to suppress all blood signal, including capillary part.
Yeah, but why do you want to suppress that? You want to that's laminar specific. So why would you want to suppress that?
Because here we wanted to create a contrast between tissue and blood. So the tissue, ideally we want to like a tissue is not suppressed at all, but all the blood signal should be suppressed.
Well, not the arteries that run perpendicular to
because here we want to extract the intravascular blood signal. If you don't suppress capillary signal, you will only extract the blood signal from large vessel. That's not good.
But the arteries you won't suppress, right?
Arteries we will suppress. So
Why?
we will suppress all blood signal because if you apply this blood suppression, it will suppress the blood not only in large vessels but also small vessels, and those suppressed blood will flow into capillary. So all the blood.
But it only suppresses the blood that flows in the direction of the gradient, right? If it flows perpendicular to the gradient, it is not suppressed.
So yeah, theoretically, theoretically, if it's perpendicular to the gradient direction, it will not be suppressed. But because this is like a blood suppression, applied throughout your acquisition, for example, your repetition time, which is 4 seconds. So there will be always some time points those blood flows to some direction which is not perpendicular to your gradient. It will experience those suppression. So as long if it's suppressed, then it will stay. So yeah. So the gradient has a direction, but the blood vessel, it has all kinds of direction. So it will always so the blood flows everywhere. It will always experience those suppression. If the blood vessel it only has one direction, then we will have problem here. Yeah.
Yeah, but you excite new magnetization with your readout pulse, right? And you also excite some relaxed blood.
Relax the blood. So
well, yeah, if your pulse angle is not 90 degrees, right? So
no.
Not everything is saturated.
So this is like a simulation, based on our free angle, that. Yeah.
I have a question, maybe about MT effects during the Dante. Basically, the preparation module is kind of having these bimodal pulses. With gradients and without gradients. So even for your vapor contrast, you would have a kind of an MT contrast to some degree that would suppress the vapor contrast, right?
So that's like a question I think also from previous ISM, so MT, so for those binomial pulse, you definitely has this MT effect. But for the Dante pulse, when you have a gradient, does it has an MT effect? I would say so. When you for those pulse, for those binomial pulse, so it works as an MT because if you do a simulation of those, it has a saturation band at some on-off resonance frequency. But if you add a gradient at the same time, basically in each voxel, inside the voxel, in the tissue. So in the tissue, if you don't have a gradient, the tissue will stay at its own resonance. But if you apply gradient, the tissue will also have a frequency distribution, like not only just stay at a frequency equal to 0 normal frequency, but also across a bunch of frequency. Basically, you will have all those like inside your voxel. So so it will, for example, if you apply the Dante, it will basically Dante itself is some kind of, it has a lot of like a saturation band. It has saturation band within your tissue signal. So if the tissue, if something flows, it will suppress it. It's not a selective saturation to add some off resonance frequency. So it's different compared to the MT like a pulse, binomial pulse.
Because it's a global suppression and not kind of.
Yeah, it's a global suppression. It's a global. It will have some global suppression. It will generate some, I would say, some like a T1 effects. But compared to the MT pulse, like without gradient, so without gradient, if we like do diffusion, you see the residual still have very strong like those kind of tissue contrast, which is mainly contributed by MT. But MT, those kind of tissue contrast, you are right. It's a little bit. It's also partially cancelled a little bit by the Dante pulse. But I don't think that's because of the Dante has the MT effect. It's some other effect.
Have you ever tried to do the MT only, like MT bold instead of the Dante, like this ABC kind of thing that
yeah. So theoretically you can, right? So theoretically MT will suppress the tissue, so you will also generate a contrast between tissue and blood. It will also sensitive to CBV change. But the issue is the sensitivity. So you can see here MT enhanced the original VAPER by like 30%. So which means like MT, like those kind of theoretically the sensitivity, the MT like fMRI sensitivity is around 1/3 of original VAPER. And the original VAPER is already 1/3 of sensitivity of the bold. So you can do it theoretically, but in reality it will have a very low sensitivity.
Unless you kind of use it together with bold, like David Norris suggested.
But the previous paper, like in Sonji Kim's group, if you combine MT with bold, so if you combine them together, like here we actually already combine them together. Like if you combine them together as shown the red curve, you are still dominated by bold. So in the previous animal paper, when they combine MT with bold, they can increase the specificity inside inside the gray matter, but the superficial bias will not go away. So yeah.
Would you think that the MT approach for the kind of control image would be similarly helpful for VASO?
I think so. It's you don't. It's a preparation, and it's actually very like time efficient because we applied like every 0.2 milliseconds. So for example, 100 milliseconds you can apply 500 pulse. So it's it take like a very little time. So
I have another question. So assuming that this dynamic division is fine, like we will get rid of this T2 star weighting, like assuming that. So the contrast that you are dealing with here is basically like CBV divided by 1 minus CBV.
Yes.
Is this correct?
Yeah, it is correct. There's some CBF term, but we will not cancel
out.
Yeah,
sure. I am just
the CBV term is a CBV divided by 1 minus CBV. Yeah.
Okay. So and CBV values are fractions, right? Like between 0 and 1.
Yeah.
So now I was thinking in VASO, in VASO's dynamic division approach, you like approximate to 1 minus CBV fluctuating up and down. So in your contrast, I mean, assuming other stuff is like fine to divide and so forth, you have this strange like CBV divided by 1 minus CBV contrast. Did you Like, have you thought about it? Because there would be a way to make it more similar to VASO. Like if you divide.
Yeah. If you do it opposite, it will be similar to VASO. So it doesn't change the contrast mechanism, but you can divide MT by density or density by MT. It's the same. Like it's the same. It's just how you like report your results. Like it's basically if you reinforce this image, it will be very similar to the VASO image. It's the same. But I report it in this way because so if you like divide in other way, there will be a lot of like zero, like for example, so those blind will become zero. And in fMRI analysis, you usually report your signal change as a percent signal change. So if you have a lot of voxel signal close to zero, those percent signal change becomes a lot of like spatial spikes. So
yeah, I get it, but like it connects to some other thought. So at the beginning, before this slide, you said that if you proceed with like acquiring CBV and 1 minus CBV data, you would double your sensitivity because now you're measuring the same thing twice.
If you either will the contrast between those two will be doubled.
Yeah, okay. However, now I'm trying to understand your results based on your comparison between MT VAPER and well, it's not like double, right? It is some percent increase. Have you
some percent? Yeah. In the model way, we simplify just take the difference because if you do the division, it's kind of difficult to understand it. But basically, the contrast between those two, like in a model, will be double if the tissue can be suppressed, can be fully suppressed.
Yeah, okay, so by this, now I will tell you my gut feeling why I'm talking about these things. So in your dynamic division approach, if you do like CBV, like one of them divided by the sum of the other two, like, and if the multiplier term is the same, you would similarly get rid of this T2 star multiplier term, like rather than dividing one to the other, but like divide one with the sum of the two. And then that would give you something basically, assuming all the other stuff is correct, like literally the same as the VASO contrast. And I think there might be some numerical issue there that might give you a bit more sensitivity and more comparable contrast directly to VASO.
Okay. Yeah, thank you.
Do you see what I mean? Like,
so
I can send you an email later.
Okay, that'd be great. Yeah, thank you.
Maybe for the people aside of Yuhui, so Yuhui has like started the VAPER at NIH before, and we are allowed to send sequences back and forth. And whoever wants to use something like this, we have a early version of this, and maybe we can even get a kind of the latest.
Sure.
So let us know if you want to run this here on the Terra scanner. I think it would not be too hard to get it for 70A too, I assume. But we have it on the Terra. All right, if there are no further questions, then thanks a lot, Yuhui, for showing this. Good luck with the last round of revisions. And I'm looking forward to see you in 2 weeks when Grace Edwards will talk about layer-fMRI VASO in visual cortex evoked with language tasks. See you then.